Welcome back to the another class of fundamentals of particle and fluid solid processing. In this class we will be continuing with our concept on this fluidization and relevant particle properties, as well as how this influences the fluidization characteristics. So, we started with the concept of different types of powder, okay, or very fine material. So, it was Gelder, a famous researcher and scientist, who initially classified these powdery materials into, or these whole particles, the segments of different particles that is used for fluidization, into 4 categories based on its fluidization at ambient conditions. These categories are Gelder's group A, group B, group C and group D particles. Group A particles, okay, these are the particles where the non-bubbling fluidization happens, followed by bubbling fluidization with increasing velocity. If you remember the concept of bubbling, the boiling bed, okay, the bubbles formation, even that the point we mentioned about the analogy between the boiling pool of liquid and when the fluidization happens through solid particles. Okay, you must now remember or recall the difference between the aggregative fluidization and particulate fluidization. So, the group A basically exhibits this non-bubbling fluidization at the lower velocities, and as we increase the fluid velocity, superficial velocity, the bubbling regime starts. In group B type of particle, on the same operating conditions that we discussed for the group A, we have no bubbling fluidization, only, sorry, this is the only bubbling fluidization, I mean no non-bubbling regime that is there for group A. Okay. Unlike group A, in group B there will be no non-bubbling regime or smooth fluidization, there will be only the bubbling fluidization for such particle on the same operating condition as of group A fluidization. Group C are very fine, they are cohesive powders, and basically these particles are incapable of fluidization. So, those particles are very fine, powdery in state, they have cohesive bonds, they are incapable of fluidization, they are categorized as group C particles. And group D particles are relatively larger size particles that produces deep spouting beds. Okay. In spouting bed, what happens? You have this fluidization, the flow happens like as if there is a single point of entry, and the whole gas bubbles, the gas flows and it flows very vigorously, the particles mixes very vigorously inside that. Even in fluidization that happens, but it happens as if there is a single point entry. Okay. Now, we will see these categories in details further. Okay. So, once again we have 4 category of fluidizing material based on their fluidization characteristics at ambient condition. They are categorized in these categories, that is group A, group B, group C, group D. Group C particles are typically incapable of fluidization, these are the very fine particles, okay, powdery state material. Group D are of relatively larger size particles or the materials we have. Okay. So, what happens, this is basically the schematic of that different types of particles that are categorized in group A, B, C, D, okay, and their relative density. So, very fine region, okay, very fine particle, and if it has very higher relative velocity, they fall in this narrow region of group C material. Having the similar condition, if the particle size increases, okay, their interparticle forces and all these things becomes less dominant, okay. The inertia forces actually acts more and more on those particles, okay, and then this comes to the region A particle. With further larger size and this higher relative density region, we have group B particles, and further increment with the particle size, we have the larger size material, which is group D materials. So, the point is that, let us say this category at ambient condition, okay, does it mean that group C particle can never be fluidized? It can be, but at a different temperature and pressure. If you can alter the surface properties of these materials, okay, the surface forces becomes less dominant, okay, the cohesive nature becomes less dominant, the inertia of these particles becomes prominent, and then the particles can be fluidized. So, the influence of temperature and pressure on this particles agglomeration, conglomeration, particle grouping has tremendous influence. So, a system, okay, that is non-fluidizing at a certain condition can be fluidized at a different operating condition. That operating condition can be changed with the temperature and pressure, or some mechanical vibration, some mechanical agitation. I mean, this is the additional forces you can provide, a stirrer, a similar kind of external forces that you can provide to make it fluidized. But this is the broad category at ambient condition based on their fluidization property. So, this window of this non-bubbling fluidization in group A particle is relatively small, okay. In bubbling fluidization, okay, this is the most frequently encountered in gas solid system, okay, and that is why it is very much frequent in chemical several commercial applications. Since this range of gas velocities are lower with group A particle, okay, or typically if you have seen the characteristic that particle B or the group B, okay, there is no option, or let us say the no window of non-bubbling fluidization, only bubbling fluidization happens there at ambient condition or at general condition, which means in commercial application what happens? You typically have high throughput, you require high throughput, okay, and then in the gas phase, if you remember again the aggregative fluidization, okay, there immediately the bubbling fluidization starts. So, the most commercial applications are happening in this bubbling fluidization region. Now, this bubbles appears at minimum bubbling velocity, which is different than the minimum fluidization velocity, which is designated here as UMB. B stands for the bubble. minimum bubbling velocity is here designated as UMB. There are several expressions from the literature. Again, correlations have been proposed after several experiments with a lot of different types of particle, different conditions, okay, and then researchers have proposed such relation. This is one of such relation to know or to determine what is the minimum bubbling velocity, okay, which has a parameter F. It is nothing but the fraction of powder that has the mean diameter less than 45 micron. XP is the mean size of the particle, okay. The other parameters are known for us. So, similarly, there are several relations that are available, like the minimum fluidization velocity. Similar to that, we have minimum bubbling velocity, the point where the bubble starts to form from non-bubbling region to the bubbling region. So, group A particles are ideal for fluidization because it has the complete regime. You can say that it can be operated in the non-bubbling regime or in the bubbling regime, although the window is relatively smaller, but still you have it in this case, unlike the group B particle, okay. So, there is the window of non-bubbling fluidization. In this case, the bed expansion is very high. We have high solids mixing, high gas back mixing, okay. The examples of group A particles are the catalysts that are used in cracking operations in petrochemical industries. Now, group A particle has another characteristics where, as we have mentioned, that there is the onset of bubbles because there is a window for non-bubbling regime as well as there are the bubbling regimes. Now, at a relatively higher velocity, there is the continuous formation of bubbles, it splits, its coalescence happens, okay, and that helps us in having a smooth fluidization. In this case, you can have the maximum size of a bubble which is stable. In group A particles, you can have the stable formation of maximum diameter of a bubble, of the biggest size that is possible to form there, that is stable in condition. Okay. So, these are the characteristics of group A particles. In group B particles, okay, at minimum fluidization velocity, we have onset of bubbling because there is no window for the non-bubbling fluidization. We have moderate bed expansion, relatively lesser than the group A particles, relatively lesser mixing of solids as well as lesser gas mixing than the group A particles. The example of this group B particles are, let us say, the sand particles, the building sand particles. Group C particles, as we have already known, that these are difficult and these are categorized because these are incapable of fluidization. These are cohesive in nature. Okay. If you try to increase the flow superficial velocity, okay, there will be no bubble formation. The flow will just channel. Okay, it will be channelized at a certain portion. Okay, like if this is your material that you have, the flow can be bypassed, kind of making a fracture through those solid particles, a stack of solid particles. It will bypass through only one section. Quite naturally, you do not have required mixing of the solids. You do not have gas back mixing. The examples of group C particles we already mentioned are, let's say, the flowers we have, wheat, cement, this kind of material. Okay, so virtually there is no expansion due to this channeling effect. Very poor solids mixing, very poor mixing if you require in such bed. Naturally, poor heat transfer, mass transfer, everything is involved in there consequential way. Group D particles are coarser materials or the coarser particles. Okay, as the size increases, there at a particular or at the same operating condition, there is low bed expansion, there is low solids mixing, but better than group C particles. We have low gas back mixing. The examples are like gravels, coffee beans, and something like that, which are bigger in size. Fine. So I hope this categorization is now clear to you, that what is Gelder's group A, group B, group C and group D, how they will behave in fluidization, and which one to choose and why for ideal fluidization. So if we go into this further, this group A material, for a condition that is the minimum bubbling velocity, when that is higher than the minimum fluidization velocity, okay, as we have mentioned, that this kind of scenario that happens, that in a bed this bubbles forms because we have reached minimum bubbling velocity, and then there are coalescence, splitting, everything is happening continuously throughout the bed, and this helps in having smooth fluidization. Okay, or you can say in other words, to understand the scenario more clearly, kind of let's say the uniform or homogeneous fluidization. For group B and D, these groups, the minimum bubbling velocity is itself the minimum fluidization velocity. As we reach the minimum fluidization velocity, you hardly have any control to operate that in non-bubbling regime. The bubbling regime starts. Now, as the bubble continue to grow, now this poor fluidization occurs, okay, with large pressure fluctuations, because the bubble grows and grows and it ultimately may burst at the surface. So that is why during the discussion of particle or group 1, I mentioned that the maximum size of the bubble in a stable condition that you can achieve there. Here the bubbling regime starts, but it continues to grow, okay, and it collapses at the surface. It bursts onto the near atmosphere or the near environment, okay, and that leads to huge pressure fluctuations, which is detrimental for any commercial application. Okay, such high pressure fluctuations, they cannot afford that. The group C particles, the interparticle forces are dominant compared to the inertial forces that is acting on the particles by the fluid material or the fluidizing material or the fluidizing fluid rather. These are unable to achieve the separation between the particles, and that is why this channeling happens, because it sticks to one another due to these interparticle forces, okay, and the pressure across the bed is less than the apparent weight of the bed per unit cross sectional area, always in such cases, in such group of particles. And then, which means if you cannot visualize a bed, that what are the type of this particle that I am fluidizing, if you want to detect that, okay, and if you cannot visualize the bed, then this is one of the criteria that if you plot the pressure loss across the bed, okay, you will see, or you can detect the scenario that this pressure loss is always lesser than the bed apparent weight of the bed per unit cross sectional area. If that happens, you can sense that this particle is group C type of particle for your operating condition. You must change the particles, or you must choose different types of particles for your operating condition to have a fluidized bed, because you cannot fluidize group C particles, okay, they are non-fluidizing in that particular operating condition. Either you change your operating condition, make it fluidized, or if you have to constrain or restrain to that particular operating condition, you must change those particles, and this is an indication that if you cannot visualize what is happening inside the bed. Now, as you increase the gas velocity, or let us say the fluid velocity in such particles or any kind of, let us say, particles, there will be onset of slugs. Slug means, I mentioned last time, that there is a kind of pockets of solid materials and pockets of gas. And this kind of flows will happen sequentially. So, this onset of slugs are typically determined by the size of bubbles when they are greater than the 1/3 of the diameter of the equipment. So, it basically occupies most of the spaces in the equipment or in the vessel where you are having that fluidization or you are doing that fluidization. So, the size of these bubbles when they are greater than the 1/3 of this diameter of this equipment, that is, you can consider that the onset of slugs, and then this kind of scenario will have significant pressure fluctuations. Okay, which are typically to be avoided. But these slugs are unlikely to be developed in sufficiently shallow beds, the bed of depth lesser than a critical value. How do we determine what is that critical value? Again, the research results are here, the correlations of the expressions are there, where HMF is that critical height, okay, that relates with the diameter of the bed. So, if we strictly maintain this condition, we can avoid this onset of slug in the vessel that we are operating for fluidization. Now, this slugging phenomena can occur on exceeding the gas velocity UMS and beyond this critical bed depth, where UMS is defined in terms of minimum fluidization velocity and this critical length, critical depth. So, these are the strict conditions that if we maintain, we can avoid the slugging operation, which is detrimental for the whole operational safety, because there is larger pressure fluctuations. So, operational safety can be compromised if such pressure fluctuations happens. To avoid that, which means we have some conditions, some expressions, some restrictions, if we follow, we can avoid this onset of slugs in fluidization. So, the point is that you need to remember this, we discussed also, that in shallow beds, okay, you can avoid the slugging operation or this onset of slugs or the formation of slugs. So, I will stop here for the moment, and we will be seeing with you in the next class with the types of fluidization. Okay, the different types of fluidization, that we will go into the details, like the non-bubbling fluidization, what happens there in details, and the bubbling fluidization, how do we estimate what would be the depth or what would be the height, what would be the voidage at a certain point of time. This kind of discussions we will be having in the next class, and also some problems in the forthcoming class of this section. Okay, I hope you have understood till this much whatever we have discussed on fluidization, and I will see you with the next class shortly. Till then, thank you for your attention.